Good morning. Today I'm taking a class on CS 544 Organic Chemistry 4, Unit 1 and Methods in Organic Chemistry. Okay. So in this new chapter, new unit, I'm giving about the methods in organic chemistry. Generally, we have to study about reduction and oxidation here. So here, reductive reactions. First, we'll take up reductive reactions. Okay. We know everybody knows that reduction is generally, normally it is addition of hydrogen or removal of oxygen like that. So in organic synthesis, you can apply the reductive reactions by three types of reactions. Okay. So first one is catalytic, catalytic, catalytic hydrogenations. Okay. So here it takes addition of hydrogens. So in presence of catalyst. So for example, generally hydrogens you that in presence of catalyst. So here in this unsaturated compound is converted to saturated. Okay, saturated system. So in this case, hydrogen is added. So in presence of a catalyst with olefinic compounds. So this is about catalytic hydrogenation. So this is one type of reductive reactions. This is one type of reduction reaction. And second one is dissolving metal reductions. Okay, dissolving metal reductions. So here reduction takes place in presence of a catalyst metal and catalyst is a metal and presence of solvent. For example, say carbonic compounds, say metal in presence of say proton donor. Okay, proton donor is generally solvent. Proton donor. So this will be these ketones to be converted to secondary alcohol. Okay. So here also addition of hydrogen takes place by transfer electrons. So proton is donated by some solvent like water like this. So this is the second type. And there are another types, so there are four types, so I'm giving another one. So fourth type one. Third one is reduction with hydrides. Okay, hydride reduction with hydrides. Third one is metal hydride reductions. Metal hydride reductions. Okay, reductions. So here in this case, transfer of say, hydride from metal. So for example, say I'm giving one example, say carbonyl, the hydride transfer, hydride. Okay. So here you can say, for example, lithium, aluminum hydride. It becomes some in presence of some solvent, say like proton donor. So here also same case, this carbonic compound is converted to secondary alcohol. Okay. So this is a third type reductions of metal organic substrate by using metal in the metal hydride. Okay, this is lithium aluminum hydride. And fourth one is by hydrogen reduction. Okay, hydrogen reduction. So here, so we have fourth type here. But similarly, you can have use these carbonyl groups in presence of, say, let's for example, hydrogen hydride. Okay, hydrogen hydride in presence of some solvent, okay, like ethanol, like this. So this converted to, so here removal of oxygen takes place. So addition of hydrogen, removal of oxygen. So here carbonic compounds convert to methylene compounds. Okay, so this is step one. So what I want to say that we have four types of reductive reactions to study in this synthesis of organic chemistry. Okay, in organic synthesis. So we'll study one by one. So we have four types. First one is catalytic hydrogenation, and catalytic hydrogenation means reduction in presence of a catalyst, hydrogen added, hydrogen takes place in presence of catalyst. And second one is dissolving metal reduction. Here, reduction takes place in presence of metal along with a proton donor. Okay. And third one is metal hydride reductions, where hydrogen takes place using lithium, of course, metal hydride, okay, like lithium ion hydride in presence of a solvent. And fourth last is hydrogen reduction, where these carbonic compounds are converted to active metallic compounds. So these are four types of reaction we have. Now let's see one by one. Okay. So let's say study first one, catalytic hydrogenations. Let us study this one in detail. What are the catalytic hydrogenations? Say catalytic hydrogenations. Addition of hydrogen in presence of a catalyst. Okay. Catalytic hydrogenation. So here, catalytic hydrogenation can be divided into two types. One is homogeneous, another one heterogeneous. Mostly heterogeneous catalysis are usually takes place here in this. So here, catalysis in the heterogeneous catalysis take place simply by stirring or shaking the organic substrate solution with a catalyst in an atmosphere of hydrogen gas. The hydrogen gas may be bubble or maybe through the reaction mixture. Okay. So let's consider the heterogeneous catalysis. Okay. So catalytic hydrogenation. First, let's say what are the catalyst use? Catalyst use. Okay. So there are many catalysts are used for this catalytic hydrogenations. For I say noble metals are also used, and then the noble metals as a catalyst. Noble metals are used as a catalyst. Runny nickel. Simply you can say RNR, ANI. Okay, runny nickel as a catalyst, and some are used as a other also these are for heterogeneous catalysis. Catalysis used for homogeneous or heterogeneous catalysis. And for homogeneous, Wilkinson catalysis is used. Wilkinson's catalysis is used for homogeneous catalytic hydrogenations. Okay, catalytic hydrogenation. And for heterogeneous catalytic hydrogenation, you can use double metals, runny nickel, etc. So these are mostly used. Noble metals can be used can be again noble metals again can be noble metals can be used in different ways. Okay, first one is a finely divided metals like noble metals like say platinum, more generally platinum 4, or you can say platinum 2 are used for in the form of platinum oxide are used for number 1, okay, as a metal. So second type is by palladium or say palladium, rhodium or rutheniums are used in presence of some inert solvent, in presence of some inert support. Okay, inert supports like say carbon charcoal, barium sulfate, calcium carbonate, etc. Okay, these are in presence of on the surface of this. They absorb on the surface of this one. Like carbon are used. Here in this case, second method, these palladium, rhodium, ruthenium are used in presence of some support. Okay, and third one is runny nickel. Runny nickel is used nickel, which can be used pass is an alloy of aluminum and nickel which dissolve in. So here this prepared, you can say this prepared in situ, in situ in one port reactions, okay, in situ by dissolving by dissolving this alloy, aluminum nickel alloy, aluminum nickel alloy. Okay, I'll just write on the upper. Okay, I'll write here. Nickel alloy by dissolving in the sodium hydroxide in alkali, so that aluminum dissolves and running nickel, this nickel in sodium hydroxide solution. Sodium hydroxide solution. So here aluminum dissolves, and nickel is left out. Okay, nickel left out. Okay, so this nickel is used. So this is also one of the methods for using this the catalyst are used. We have two types. One is the platinum in the finely divided form without any support, and the second one is palladium, ruthenium, rhodium in presence of some inner supports like carbon, potassium sulfate, and carbon, etc. So these are used, and in the case of running nickel, it is fast prepared by using in some aluminum this aluminum nickel alloy in sodium hydroxide solution. So here aluminum dissolves and nickel is left out. So this nickel is used. And some other homogeneous or heterogeneous catalysts also used, like nickel boride. Also used here like nickel boride. Some other catalysts also use nickel boride, CNI, B2 is also used for this, which is more reactive than this running nickel, more reactive than running nickel. Okay, it's more reactive. Nickel borides are more reactive. But these are about catalysts used in catalytic hydrogenations. Now let's see, next is about solvent use. Solvents, the catalytic use are in the catalytic hydrogenation use are the water solvents use. Okay, solvents used in the catalytic hydrogenations. These are water can be used, and that is ethanol. Some proton donor also like acetic acid, and acid also, and some other like this also. Many can be used like and then cyclohexane, and etc. Okay, in some solvents. So in presence of water, mostly water ethanols are mostly commonly used in this case. And temperature, temperature is employed is generally in room temperature. Reaction takes place. Generally, reaction takes place at room temperature. Okay, at room temperature, but sometimes maybe heated also. In some cases, heated and overheated. In some cases also. And hydrogen gas is bubble. Most generally, hydrogen gas is bubble, and reaction condition is low pressure. The pressure also, some reaction conditions like it can be either at low pressure, or pressure can be employed as low or high. Generally, high pressures are employed for running nickel. In the case of running nickel catalyst, so we use high pressure, and for palladium, charcoal or ruthenium, low pressure are used. High pressures are mostly nearly more than 100, around 100 to 300 atmosphere. Okay, and this is below, low pressures are below 100 atmosphere. Okay, it's generally around 30, 20 like this. So the reaction can take place. Reaction condition is how to mention that the organic substrate is first dissolved in the solution, in solvent to make a solution, and then catalysts are added by just reaction takes place by stirring or by checking. Then hydrogen gas is bubbled into the reaction mixture. Okay, reaction condition is very simple. So hydrogen gas is just bubble into the reaction mixture. Okay. Some examples I am giving. Many examples are here. Some examples. I'll give one example. Okay. Say like phenyl, CAs, ones CAs, CO2ET. Say in presence of hydrogen in 1 atmosphere, the low pressure and low pressure at palladium charcoal at room temperature, okay, 30 degrees Celsius. So here only this saturated compound, the whole body is used like this. Okay, this is a product. So here palladium in presence of inert solvent charcoal or carbon at a low room temperature or nearly 30 degrees Celsius. So reaction takes place like this. If you use running nickel, then you can have high pressure. Okay, so like even this one, CSO, so running hydrogen around 100, 250 atmosphere, 250 atmosphere, the running nickel and heat around 90 degrees Celsius. In presence of solvent is ethanol. Okay, so here the bubble is like this. You can get. Okay, so I'm giving you so many examples here. So I'm telling that. So if you use running nickel, it will be temperature will be high as well as the pressure also will be high pressure. If you use palladium charcoal or platinum, then the reaction takes place in low pressure. Okay, at that pressure also at room temperature. Now let's come to the mechanism of the catalytic hydrogenations. Okay, mechanism of catalytic hydrogenations. Mechanism of catalytic hydrogenation. So here, so it takes place. This catalytic hydrogenation can take place in 3 steps. So I just so for the mechanism of catalytic hydrogenations. So let's take example of olefinic hydrogenation. Okay, catalytic hydrogenation of olefinic compounds can take place by 3 steps. So generally, first step is absorption of the organic substrate or compound molecule to the surface of the catalyst. Okay, so the first step, surface of the catalyst. Here the hydrogen also, here the hydrogen atoms may also be absorbed, on the surface of the catalyst, simultaneously or not. Okay, on the surface of the catalyst. It might be stepwise or it might be simultaneously. The second step of the mechanism is the transfer of hydrogen atoms to the organic compound. Okay, organic molecule takes place. So in the third step, after migration, transfer hydrogen atom to the organic molecule. Then third step is desorption. Takes place to give the final reduction product. Okay, so there are 3 steps for the mechanism of catalytic hydrogenation of olefinic compounds. Here, this step, okay, here in the case of olefinic compounds, the hydrogenation takes place on the cis addition takes place on the same on the less substituted side of the compound. Okay, so I'll give one examples here. Let's see the examples. So here, so addition takes place on the cis addition takes place on the less hindered side of the alkene. So let's say, for example, this compound. Okay, let's say this one plus the catalyst. So let's say this will be the organic substrate. This is the more bulky side. Okay, this is the less hindered side. So let's say first is this is equilibrium. Okay. So first step is absorption of this compound on the surface of the catalyst. Okay. Okay, this one. This is a pi bonded. You can say pi bonded. Here you use simultaneously or stepwise hydrogenation. Hydrogen can be there also on the surface of the hydrogen also can be just absorbed on the surface of the catalyst. Okay, this is catalyst. So hydrogen is also absorbed on the surface of the catalyst. Like this. This is pi bonded. And then second step is transfer of hydrogen atoms like this. Okay, so here, so in this way you can have this is the another hydrogen. One hydrogen is transferred here. C this bulkhead will be here. Then this hydrogen, one hydrogen is transferred, so like this. So hydrogen is transferred here, then another hydrogen here. Okay. So this is the second step. Second step of transfer of hydrogen atom. This is called sigma bonded complex. Okay, intermediates. So here this more again this finally this another hydrogen atom is attack here. Hydrogen atom attack like this. So we got C is a more bulky group, and then hydrogen here plus the catalyst, free catalyst here. This is catalyst and this is olefinic compound. Okay, so this is catalyst, this is alkane. Okay, now saturated compound. So this is the mechanism. So I'm repeating again. So when olefinic compounds are hydrogenated, it produces a catalyst. So mechanism is the organic substrate is absorbed, first step is absorbed on the surface of the catalyst to give a pi bonded structure of intermediate. Simultaneously or stepwise, hydrogen can be also absorbed on the surface of the catalyst like this. So it is intermediate. So once, okay, this is here. So once this form, then transfer hydrogen atom takes place. So migration of transfer hydrogen atom takes place to the organic molecule. So you got a sigma bonded first. This sigma bonded. Then next another hydrogen atom also attached. Then you got a final product, alkane saturated compound along with the catalyst. So this is the overall mechanism of the catalytic hydrogenation of alkenes, olefinic compounds. So similarly, in some cases, isomerization also can take place. I'll show you another example for how isomerization takes place in this type of reactions, in this mechanism. So isomerization of reactions can take place. Okay, here, so for example, say this is compound. Okay, let's say this one, the hydrogen here, one hydrogen. Okay, so let's say 1, 2, 3. So with catalyst, surface with catalyst. So let's say hydrogen. So here hydrogen should be isomerization maybe take place. Let's see how it takes place. So while the absorption takes place on the surface of the catalyst, hydrogen is absorbed. Okay, once let's just say this side is catalyst, surface of the catalyst, and then this is hydrogen and this one. Okay, so here, so hydrogen also, and then this is pi bonded. Okay, pi bonded, and hydrogen also absorbed here. Okay, you can see this. Okay, so here all this organic substrate going to be reduced or isomerization. Let's see how isomerization takes place. This is the catalyst. Okay, when I absorb on the surface of the catalyst, hydrogen are absorbed, as well as the water molecule also absorbed on the surface of the catalyst. So this again transfer of, now second step, transfer of hydrogen takes place like earlier one case like this. So you can transfer hydrogen. So you got one sigma or okay, sigma. So you can have hydrogen here, C, hydrogen here, and sigma bonded. The hydrogen. Okay, this is sigma bonded. Okay. The earlier one. Okay. In some cases, this also can take place. Another one is when you migrated this one, the isomerization can take place in this way. So here migration takes place to give C here. So here migration or this one coming in this way. Okay. So I'll show you this. Another method is C. This is pi bonded here. See 1, 2, 3. This is catalyst surface, catalyst, pi bonded, and hydrogen. Okay. Here this hydrogen is. So here is the isomerization take place from now the bubble is shifted from 1, 2 to say 1, 2 is having hydrogen double bond here in the 1, 2 position. But now here this is shifted to 2, 3. So let's say this is A, structure A, this is B. So now this also can have another structure like, so it can have another structure. So I'll show you another structure. This compound can have like this. I'll show you. Okay, this is A, B are here. No, another structure it can have is a catalyst. Okay, another structure, the hydrogen are absorbed, and this double bond here, and this is like this. Okay, sigma bonded and pi bonded compound. 1, 2, 3. Okay, so you can have this one. Hydrogens are absorbed as well as the organic compound is absorbed. So this you can say another structure C. This can have similarly. It can have also here same case. You can have C. And then C here, this is the surface of the catalyst, and hydrogen here, and isomerization takes place. Okay, 1, 2, 3. Double bond is 2, 3 positions, and here pi bond there. Okay, so like this you can have an hydrogen here. These are same, so you can have. So now loss of this hydrogen atom can attack. Hydrogen atom can attack here. Then you can have final product. Okay, so here C hydrogen and C hydrogen here. Okay, C and then double bond C. So 1, 2, 3 plus catalyst. Okay, free catalyst. So here what I want to say that product and then the starting materials are now isomeric form. So the isomerization takes place by sometimes also. So here the bond is between 1, 2, but here final product is between 2 and 3 like this. Isomerization can take place by hydrogenation also. This is another mechanism. So I will give some examples for even triple bond compounds, not only olefin compounds. Triple bond compounds can also undergo say like this. Say let's say CH2, and let's say serpent Here also CH2 7 CO2 ET. Okay, CO2 ET. So when you undergo hydrogenation in presence of palladium charcoal like this, they also give this cis compound, cis olefinic compounds, CH2 7 CO2 ET. Here also same case, CH2 7 CO2 ET. Okay. So what are that? Here cis olefinic compound got a compound. Okay. This can also undergo further reaction. Catalytic, it can go hydrogen plasma charcoal. So to get the saturated compounds. So this is one example. What I want to say is that triple compounds can also be reduced by using this catalytic hydrogenation to give the cis olefinic compound. Cis olefinic compound, they can undergo further reduction if you use excess of this compound. Okay. So these are all what I have talked about. All this about this are for heterogeneous catalytic hydrogenation, heterogeneous system. So now let's come to catalytic hydrogenation in homogeneous. Okay. Catalytic hydrogenation, catalytic hydrogenation for homogeneous system, homogeneous, okay, homogeneous system. So here the best catalyst used is Wilkinson catalyst. We have Wilkinson's catalyst. The most WC. Okay. So Wilkinson catalyst used for homogeneous catalytic hydrogenation. So here this is known as 3-triphenylphosphine, 3-triphenylphosphine, rhodium chloride. You can say 3-triphenyl, phosphine. This is called phosphine. 3 means 3. Okay, 3-triphenyl phosphine rhodium chloride. So this is the complex. Okay, you can see another one is 3-triphenyl chloro, 3-triphenyl phosphine rhodium like this. Chloro, you can write chloro, 3-triphenyl phosphine rhodium chloride. So commonly it is known like this. So this is the Wilkinson catalyst, which is widely used for reduction of. So it is used widely for double bond compounds, olefinic compounds. So here Wilkinson catalyst prepared generally commercially. It is available, but it can be prepared from by reacting with rhodium chloride, H2O water hydrated 1 plus in presence of triphenyl phosphine, H3 excess. Okay. So by reacting rhodium chloride with triphenyl phosphine in reactions in presence of ethanol and reflux, you get this one Wilkinson catalyst, triphenyl phosphine, rhodium chloride. Okay, you got it. So this can be prepared laboratory in situ by reacting rhodium chloride with excess of triphenyl phosphine in presence of ethanol. Just by reflection, we got this Wilkinson catalyst. Okay, so the Wilkinson catalyst is mostly used for hydrogenation of olefinic compounds. So let us see the mechanism, how the mechanism takes place. Let's see mechanism of the Wilkinson catalyst hydrogenation. So mechanism here. Mechanism of homogeneous catalytic hydrogenation. Okay. Using Wilkinson catalyst. So the first step is, so rhodium is look like this. This is catalyst, phenyl, calcium, just like that. The rhodium structure is PP3 triphenylphosphine, and here also this is triphenylphosphine, and this is here is the chloride, and this is triphenylphosphine. So three is triphenylphosphine, rhodium RS, this is RS, rhodium chloride. This is a compound. Okay, this structure is tetrahedral DSP2, tetrahedral, structure DSP2. Okay, so this is the reduction catalyst. So now this is in presence of solvent. Okay, so like a benzene solvent. This will give solvated like solvated. Another arc-sham, PH3, and this is so one is removed. Okay, one is removed. This is solvated solvent. This you can say this intermediate. This is solvated reduction catalyst. Okay. Then next you react with this is react with hydrogen. The gas is bubble into this. Then you got this intermediate rhodium and this hydrogen, and this is solvent, and this is chloride, another hydrogen here, and this is not this one PPS3. Okay, so we got this one hydrogen, two hydrogen are this is also intermediate. So now two hydrogen atom are added. So this compound, this from this react with this olefinic compound. Let's say attack with olefinic compound. Yeah. So let's say this is attack with olefinic compound. So CH2 double bond CH R. Okay, so now you can I will show here. Okay, here. So here rhodium, hydrogen, and then this chloride, this hydrogen here, and this is PPH3, and then this another PPH3. Okay, triphenylphosphine. Then this is hydrogen, and this is organic CHR. Okay. Like this. Instead of solvent you knock out, so you got this link with this olefinic compounds, pi bond that CH2. Then hydrogen transfer here. With hydrogen transfer, you got this like this. So you get. So next step is you take this one. So you will link with this one. Okay. So let's say rhodium, and this is triphenylphosphine here, the one molecule. Another one is triphenylphosphine, PPH3, and then this chloride here, and this link with this hydrogen goes there. Okay, let's say the hydrogen here, link this CH2, and then link with this CH2, CHR. Okay, so link this CH2 is linked here. Okay, this pi bond link with this one. So now again transfer this again here, transfer, and then you got this one. Okay, so you got the final product. So I'll remove this one. Okay, so remove this one. Okay, I'll write this way. This one you can write this this another way also. You can write this another way. You can write another form. Transfer like this. Rhodium goes here, this goes like this. Okay, another way. That means pick up this. This is where CH3 CHR. Okay, you can altering. Okay, this CH3 will come here. Now here attack hydrogen CH2. If you attack this hydrogen here, then we get another way. So I'm writing now. This hydrogen goes to here, so it comes CH3. If you go attack here, then it will come CHR, CH2R like that. Okay. So now this attack here, so I'm writing this way. So now this finally the product is rhodium. So it comes to, this is, we can write PPS3, PPS3, 2, okay, 2 RaCl plus the saturated compound. So you have RCH2, this CH2 become okay, CH3. This way, or you can have, or you take by this way, you can have R, you can write RCH2, or you can write RCH, you have to here RCH2 and CH3, or you can write here. We write attack here and this is okay. So we attack here, then we'll go like this. Similarly, okay. This is the way. Saturated form, the product. Okay. In some case, you got attack here, or attack here, like this. One will go. So you got the product. So finally this goes here and then goes like this. So you got a final product. So what I want to say is that so homogeneous catalyst can be used mostly when catalyst is used for catalytic hydrogenation of olefinic compounds. So many examples are here. Many examples can be used. This is widely used. There are many examples. So I'm giving some examples. Many examples are here. I'll give some examples. Then let's finish the chapter. I'll give some examples. So for example, for reduction of this compound, and this one. Okay, let's say this one. Okay, we're using lithium. This will kissing catalyst in presence of ethanol, or some other solvent also, xylene also can be used. So now this can be reduced. This one. Only the external one is used. No, the second write CAs. These are compared to CH3 or CH. Okay, so you can write CH like this. Okay, another one. Another example is these are all natural products. Okay, natural product, carbon or some other toluene or xylene can reflux. Okay, toluene xylene reflux. So this is internal one, external one is reduced to this way. You can get CH3 like this. So this is what I'm giving examples. So this is what I'm telling about this. All this about the catalytic hydrogenation using heterogeneous or homogeneous catalysts. So this is our chapter. We have the next class I will tell you about the dissolved metal reductions. So this is the first one is catalytic hydrogenation. Okay, so today let's finish this. Okay.